welcome everybody to a new video where we are presenting a new project from, in this case, Shivesh. He's presenting the project for navigation for ROS2. We'll have a presentation of 15 minutes. He will show us a bit how it works in the real robot with a real connection, and then he'll explain a bit how he did it. Are you ready?
Yes, I'm ready.
Okay, let me check that. Okay, let me check that. Let's see the stream if it's working.
Okay.
Okay, sound.
Okay.
Okay, sound. Great. So we are live. It's all yours.
Yes. So yeah, the first step I'll do right now is to launch my ROS 2, which is a graphical visualization tool. And yeah. So yeah, the first thing I'll do is open my config, which I've already saved before for my localization. Okay. And yeah, so I'll go to my ROS2 workspace. And yeah, from here, I'll launch my localization. Yeah, so ROS2 launch project localization, and my launch for file name is localization.launch.py. Yeah, it's creating an object. Okay, yeah, it seems to be working now, fine. And yeah, so as you can see that my map has loaded. And from here, like I'll start the localization process. I'll just see my robot's orientation, like how it's where it is exactly. Okay, I'll just like make it bit more. Yeah. So it's looking towards this side. So on the left hand side towards the bottom. And I think I think this is the part I should localize from here. I should like do my 2D pose estimate from here. I'll just double confirm it. 2, 1, yeah. 2, yeah. Yeah, so right now, as you can see, this is the particle filter or particle dust. Right now, it is uniformly distributed all over the map because the robot sensor has not yet sensed the entire environment. And after I move my robot around a bit, you will see that the particle dust will clutter up together to form higher accuracy particles. They're usually like particles with more weights have like higher accuracy for their position.
Great.
Yeah, so I'll just like rotate it around. I'll rotate it like on both the sides, clockwise and anti-clockwise. So yeah, as you can see, like the map is automatically becoming better. Yeah. So right now, as you can see, like the map has become like pretty, accurate right now, and it can identify the walls and the obstacles over here. And yeah, so the next step would be like launching my path planning launch file from where I can give my 2D pose goal. Yeah, so it's like it's inside my project path planning. The launch file name is pathplanning.launch.py. Okay. So yeah, it's configuring the BT navigating server. It's okay. Started creating the bond timer. Yeah, so I think right now I can do the yeah, I can. So I'll just make the robot move somewhere around. I think over here will work. So you can see like the robot started to move. Like the goal that I gave. Maybe like I think yeah, I think if I do side by side, it will look better. Some bits. Okay. Just give it somewhere around here. Did I just press? No, to press. Uh, okay. Oh, saying no valid trajectories. Okay.
Hmm.
Oh, I think because of the obstacle in front of it.
Yeah, it's because of that, because
Yeah, the recovery
it's so
behavior.
close.
Yes. Okay. So should I just like go to my like path planning, like navigating to the particular spots?
Yes, please.
Yes, I think like so I'll just like do it for the corner one. Corner one is the one near the construct symbol. Yeah, as you can see, like the robot will try to go towards the construct symbol. Uh, yeah, actually, like during while saving the spots, I think I had recorded my spot over here, so I think it is correct. And I'll try to move it to the corner right across it. I mean, like I think that should. Yeah, so the robot is now trying to move and go. Yeah, I think there's a bit problem with the obstacles on the real
Yeah,
map because
it's
like the base is much larger than the one in the simulation, so it
uh-huh.
does not it's not able to identify the obstacle properly.
Mm-hmm.
Yeah, so as you can see, like it has successfully like reached the corner two, which is right across the corner one, and yeah, so I think like from here I can present my PowerPoint presentation if everything's okay.
Yeah, it's fantastic. Very good work. So
Okay.
if you can do the PowerPoint presentation to show us
Yeah.
a bit the code and explain us a bit.
Yes. Yeah. So yeah, is my screen visible or no? No, it's not.
No, I can't see the PowerPoint. So I
Okay.
imagine you have to share the
Yeah,
whole
I'll do a
screen.
new share. Yeah, yeah, yeah.
There,
Okay.
now.
Yeah. So yeah, so my name is Shivesh Sharan and I'm here to present my ROS2 navigations project. And the contents that I'm going to present is like basically there are four sections, that is mapping, localization, path planning system, and moving to the spots or like obstacle avoidance that is given like as per the project given in the project. And yeah, this is our existing environment. It is basically a rectangular room surrounded by walls. And we are using a Turtlebot 3, which has 360-degree LiDAR sensors. So yeah, so the very first section is mapping section and maps and navigation. It basically serves for localization and trajectory planning based on the occupancy grid maps in our ROS2. So yeah, that's as the essential component, as I mentioned before, is LiDAR, odometry, and SLAM algorithm like cartographer to facilitate the maps creation. And yeah, cartographer uses real-time SLAM, which is a new thing that I've learned in my ROS2 navigations course. It is a system which is basically developed by Google, which provides robust mapping capabilities. And for all these, we have a navigation lifecycle manager. It basically like streamlines node management for efficient navigation system operation. And yeah, so the takeaways are like maps are like foundational for robot navigation tasks. Cartographer like simplifies the map creation with its real-time SLAM capabilities. And yeah, the navigation lifecycle like manager essentially like helps us manage all those nodes and the nodes together like efficiently. And yeah, this is the like the map that I created in my cartographers using my cartographer SLAM. And yeah, so the next section is localization. So yeah, what is meant by localizing a robot in an environment? Localization refers to the robot's ability to determine its position and orientation with respect to the environment, typically represented by a map. And how are we doing the localization? So over here, we are using AMCL, which is Adaptive Monte Carlo Localization. It is basically a probabilistic localization system for 2D robot movement in ROS. So it implements the AMCL localization approach, basically using a particle filter to track the robot's pose against a known map. Like as I had shown in my live demo, those particle filters. And yeah, so there are basically like on parameters for AMCL. So the parameter categorized are into like overall filter, laser model, and odometry model parameters, which are crucial for AMCL for localization. And yeah, there's also global localization. It is achieved by distributing the particles evenly across the map and moving the robot to identify its location. And yeah, so this is basically the difference. When you just initialize the robot, the particles are uniformly distributed all over the place because the sensors have not yet gained the information and perception of the environment. So once you move the robot around, these particles automatically like cluster together to form more accurate, more high accuracy particles, which basically helps the robot to localize and move around with accurate positions. And yeah, so the third section is path planning. So exactly what is meant by path planning? Path planning involves finding a trajectory from point A to point B, like while avoiding obstacles along the way. And yeah, the nodes that we launch during path planning are the planner node, which computes the path from point A to point B while avoiding the obstacles. So controller node performs reactive path planning, which avoids dynamic obstacles and generates wheel command. And we have the behavior tree navigator node that I had mentioned before. It coordinates a path planner and controller node, and it is basically used for our recovery server node, like which executes behavior if the robot encounters obstacle or gets stuck in between that I had encountered in the live demo as I showed you. Yeah. So yeah, what are the parameters for path planning? So the three nodes that I like discussed before, the planner parameters include like planner frequency, plugin selection, and tolerance. Controller parameters include frequency, velocity thresholds, goal checkers, and recovery parameters include spin, backup, and wait. I used wait and backup, and sending navigation goals. So basically, like I'm using an action server to send navigation goals, and I'm using a topic to subscribe to it, which publishes the navigation goal. And yeah, this is like the command that I used in my live demo as well to launch the navigation goal to go to a particular corner. Yeah. So yeah, I'll just go through the algorithm that I've used for this path planning. Yeah. So basically, like to navigate to the spots, which are the corner one, corner two, and pedestrian. And so basically, like I created an action client node which sends a goal to a navigation action server. So the robot now navigates the robot. So the it navigates the robot to a specified pose or position, and then it reads the pose coordinates and orientation from the parameters that I had given it initially. Then it constructs a goal message, sends the goal to the action server, and handles the response asynchronously, because we know that the ROS real robot works on ROS 1 and we are working on ROS 2, and there's a bridge in between. And yeah, and it spins the action client node to keep it active until the goal is achieved. And yeah, how do we like save the spot? So basically, we create a subscription to the initial post topic, and there's a callback function that I created this, which is called post callback. It also subscribes to the initial pose, providing the initial pose of a robot. It listens to the initial pose of a robot, then it uses this pose in like records this pose into a dictionary, and from this dictionary, it automatically there's a line in the code that writes these initial poses into the YAML file for further navigation goal. And yeah, like obstacle avoidance, which is the final section of our project. So basically, like the key concepts are like cost map, which is basically 2D representation of robot sense obstacle on a grid map. So the importance of the cost map is helps to avoid like obstacles on a map. So there are basically two types of cost map, which is a global cost map and local cost map. And global cost map is based on static map used for long-term path planning. Local is based on new obstacle used for short-term path planning. And yeah, global cost map parameters were added in my planner server.yaml file. Local cost map parameters were added in my controller.yaml file. And inflation layer like must be added after the obstacle layer if you want to. Yeah. So yeah, these are the three corners that I had recorded during my live demo. So corner one, corner two, and corner and pedestrian, which are, and also you can see the poses of the robot at it, the orientation and position. And yeah, so the challenges is that I think that I have faced during this project is like, of course, like learning about YAML. YAML is something that I had never like heard or learned before, because I have also done ROS2 basics Python course, and in that like I've not heard, I did not use YAML. So and yeah, there's also one interesting thing about YAML is that like it like YAML files updated without the need of building the package again. So what I mean by this is that once you record a spot using a robot and you feed the spots, or as I mentioned before, the spots get automatically written on the YAML file. But if you want to use if you want to use the positions or the new spots, you have to build the package again. Because if you don't build the package again, YAML seems to use the like the values of the old spot that had been written on it. So yeah, yeah. So the next part is map, and yeah, making the map, there's difference between like the map on a simulation and on the reality. I was trying to make the map as realistic as possible, but then I realized that on the real map or the live demo map, the obstacles like are not like fixed at some particular place. It moves like all over the place. So I used the simulation map that helped me a lot better. And yeah, if there are more obstacles on the map, or the map is like not rectangular, or like it has a different unique shape, I feel that the localization can work much better, because on a rectangular room, it is like kind of symmetrical. So the robot might get confused sometimes, or you might not able to recognize where the robot is on the map and to do the localization. Yeah, I think like that's about it. Thank you.
Wow. Bravo.
Thank
Wow,
you.
fantastic. Fantastic presentation. Well, very well done. I don't have a lot of suggestions actually. It's fantastic presentation. It worked fantastic. You explained very well, and the only things that I can comment about is the YAML issue. Is something that is related to ROS2, not only YAMLs.
Okay.
It's just because when you modify something in the source folder in ROS2, it's not the thing that it's executed. So the thing that it's executed is in the build or install. It's in the install basically.
Okay.
So
Okay.
that's why you have to compile every time, which in ROS1 you didn't do that, because
Yeah.
basically it linked all the files that weren't binaries, and then you didn't have to compile all the time. But ROS2 has this failure or this feature, let's say.
Yeah.
So
Yeah.
you have to do that. But apart from that, again, an applause. Very, very good. I really love the
Thank you.
presentation.
Thank you.
And that's it. So thanks a lot. I'm going to wrap the
Yeah.
presentation.
Thank you.
So again, thanks everybody to stay until the end. It was a fantastic presentation, and see you in the next student presentation of a project. Until then, keep learning. Bye-bye.
Thank you. Yeah.